Hi everyone, and welcome to the second of two videos going through some past exam questions on rates of reaction and the Boltzmann distribution. The first video was all about rates of reaction and catalysts and that kind of stuff. This video is going to just go through the two types of question that you get on the Boltzmann distribution. I mean, there really are only two questions about this. So you can learn it and be pretty confident about what you're going to be asked to do in the exam. This is the first one. This is talking about a catalyst. So it wants us to sketch a labelled diagram of the Boltzmann distribution, label the axes, and explain how a catalyst increases the rate of reaction. Okay. So again, we've got kind of bullet points here. So it's always a good idea just to go down these and make sure we've done them all. So sketch a diagram of the Boltzmann distribution. So we need to know what shape this graph is. There are a few things that are important. It must start at 0. And then the shape of this graph kind of looks something like that. And then it must not touch the x-axis again. So that's our Boltzmann distribution. Label the axes we need to do next. So the axes, on the x-axis you have energy, and on the y-axis you have number of molecules, or number of particles, or you can word that in various different ways, but that's the gist of it. So what it's showing you is how many molecules have certain amounts of energy. Okay, and this is why it's important that it must start at 0, because there are no molecules that have no energy. And it must not hit the x-axis again, because otherwise we'd be saying that there is a maximum energy above which there are no particles that have more energy than that. And that's not something we can really say. Like, in theory, you could always heat particles up a bit more or give them a bit more energy. So there's no particular reason why every particle should have less than a certain amount of energy. So that's why it shouldn't ever hit the x-axis again. And then we need to use our Boltzmann distribution to explain how a catalyst increases the rate of reaction. Okay, so we know what a catalyst does. Let's write this here. So a catalyst lowers the activation energy for a reaction. And we could say by providing an alternative pathway, but you probably wouldn't need to write that here. It's not really relevant to the question. That would be a separate question, really. But we might as well put it in here. It's not going to do any harm. So we need to show that on the diagram, right? The activation energy is just saying, well, there's a certain amount of energy needed to react. So we can just put that anywhere. We can just pick an amount of energy and say that's my activation energy. There's no scale here, right? It's not relating to a specific reaction, really. It hasn't told us anything about manufacture of methanol. So we can just put our activation energy on anywhere, really. So I'm just going to stick this on here and say, right, that is my activation energy. There. Right, what's the significance of that? Well, if that's the activation energy, that's the minimum amount of energy needed to start the reaction. So what that's showing me is that all of these molecules to the left of that don't have enough energy to react, right? It's only these molecules here that have enough energy to react. Okay, we could label that. That would be good. Okay, so this is molecules with enough energy to react. If we're using a catalyst, we're saying it's lowering the activation energy. So we're going to move the activation energy to a lower value. So we're going to have a new activation energy that I'm going to put on here. If I can try and draw a straight line, that would be good. And I'm going to call that activation energy with a catalyst. Again, you can label this however you like, as long as it's clear, right? That's very clear what that means. EA is a standard abbreviation for activation energy. So that's absolutely fine, and I've made it clear that's for a catalyst. So what does that do? Well, you can see that if the activation energy is now here, then I've got all of these molecules as well. Now all of those have enough energy to react as well. So let's label that. Additional molecules oh gosh, my writing's gone terrible. With enough energy to react in the presence of a catalyst. Okay, so you can see there's an extra chunk of molecules there that are now able to react. Okay, and so let's write that. allows the activation to reaction by providing an alternative pathway. This means that a higher proportion of the molecules have enough energy to react. And we could also mention something about the collisions. If we've lowered the activation energy, then the collisions are more likely to be successful. Okay. So we could say a higher proportion of the molecules have enough energy to react, and the frequency of successful collisions increases. It's a bit of an odd one. Sometimes the mark scheme gives you a mark for that, and sometimes it doesn't. It seems to be a little bit inconsistent, but it's not wrong, so it's always worth writing just to be on the safe side. Frequency of successful collisions increases. I think it really just depends on how many marks they need the question to be to make the paper add up to the right number. Sometimes they have an extra mark and give you a mark for writing that. Right. Then it says, explain why the use of a catalyst can reduce the demand for energy. So this is a similar kind of question to the one we saw in the previous video, where it was talking about catalysts helping you to be sustainable because you're using less energy. They don't just want you to write here because it lowers the activation energy, because you've just written that in the previous part of the question. Right? They're not going to give you a mark for that again. We need to do something different. So this is the idea that we talked about with, because we've lowered the activation energy, we're not going to have to heat the reaction up as much. Okay, so we can say catalysts allow the reaction to be performed at a lower temperature using less energy. So just watch out for that kind of thing, and it's worth thinking about. You can't just reuse a point that you've already used on a previous question. They're not going to give you 2 marks for writing the same thing, so you've got to write something different. Okay, we said that was one of the 2 questions about the Boltzmann distribution. It will either be show the effect of a catalyst, or it will be show the effect of changing the temperature, which is what we get with this question here. Hydrogen and chlorine are reacted together. This reaction is repeated, but this time the temperature is decreased. Okay, describe and explain by drawing appropriately labelled Boltzmann distributions. Be careful, look here at this word, distributions, with an S on the end of it. So it means we need to draw 2 curves. So they do give you a bit of a clue if you look for these kind of things. Grammar is sometimes your friend. It's actually helping you out here, giving you a clue. So what's happening to the rate of reaction if we've decreased the temperature? Okay. So we need to draw our Boltzmann distribution. So we're basically going to draw that again, except we're not going to show this lowering the activation energy by using a catalyst, right? But everything else we're going to copy. We're going to copy everything in blue here, basically, right? And they haven't given us the axes this time, which is a bit annoying, but there you go. Obviously, somebody was lazy, couldn't be bothered to draw that in the office when they were doing the exam. Let's make this big so we've got plenty of room. Going to label the axes again. We always need to do that. So energy and number of molecules. And we're going to make sure that it starts at 0. We're going to draw this kind of characteristic shape. Remember, it's not a symmetrical graph, right? It's sort of shifted to the left a bit. And we're going to make sure it doesn't hit the x-axis again here. We're going to put the activation energy on, but we're not going to be talking about the activation energy being reduced this time, because we've not got a catalyst. And again, we can show that these are the molecules with enough energy to react. That's exactly the same as we did on the previous question. Okay, then let's do a bit of writing, and then we'll show what we're going to talk about on the graph. So we're saying the temperature is decreased. So describe and explain what happens to the rate of reaction. Okay, well, we know, don't we? Decreasing the temperature is going to decrease the rate of reaction. Because if we decrease the temperature, the particles are going to have less energy. Now this is where it becomes different then. The particles have less energy. If the particles have less energy, then we haven't just changed the activation energy. We've changed the energy of all of the particles, right, by decreasing the temperature. So this whole graph is going to be different. We need to draw another graph to show what's going on at the lower temperature. If we've got a lower temperature, then the particles are going to have less energy. So we're going to shift our graph left. It's going to move that way a bit. Okay. There are some things though that still need to stay the same. Okay. We want to still start at 0. So still not going to be any particles that have no energy. We still don't want to touch the x-axis again. But we want to shift our graph left a bit at a lower temperature. Okay. So what we're going to do is just squidge it that way a bit. Okay. And that means this tail is going to come across a bit. And it means actually the peak is going to move upwards and to the left. Okay. So we end up with just a more exaggerated version, really, of the shape we've already got. And again, making sure that we don't touch the x-axis again. That's still not the case. Okay. And then we need to label this to make this clear. So we want to say that this one is the lower temperature. And the original graph that we drew here is the higher temperature. It's really important that you make that clear. Don't label this like T1 and T2, because you want to label it high temperature, low temperature. Just then it's really clear. You can't possibly misunderstand that, can you? So what does that show us then? Well, it shows us then that although the activation energy hasn't changed, we've got fewer molecules now with enough energy to react. We've only got this number of molecules. Carrying on. Okay. Because the particles have just got less energy, so there are fewer of them that have more energy than that. Okay. So decreased rate of reaction, the particles have less energy. The proportion of particles with energy greater than the activation energy has decreased. That's what we've shown. We've gone from all that blue area to just this smaller red area. And so the frequency of successful collisions decreases. Again, we talked about sometimes that's worth a mark, sometimes it isn't, so let's just write it anyway. Okay. And that's it. Those are your 2 questions on the Boltzmann distribution, right? And you just want to be comfortable with, right, whenever this question comes up, you know what you're going to need to do. I'm either going to draw this and draw my 2 separate graphs, or I'm going to draw my 1 graph and just show the activation energy moving. Okay, so this is quite a nice topic. It's either that question or it's that question.